When you have very complicated Boolean expressions, one of the best things you can do is simplify them. And of course, it's always nice to have a simpler expression to work with, but it can also mean that if you want a digital circuit, a digital system to have a certain mode of operation that is expressed by your or contained in your expression, you want to have it as a simple expression as possible, because that's going to mean less logic gates. And that which means less space, less money, all good things in engineering. You always want to have a great response, or as good a response as you can get, certainly one that meets the spec, but you don't want to pay a lot for it, or certainly you want to maximize profits. Space and profits, how many parts you have, and profits tend to go together. So this is starting to look at simplification, Boolean simplification. So there are these laws, looking at identity laws or redundancy laws here, and I don't want to get too caught up in laws. I have nothing against equations or expressions. What I do have some hesitancy about is how people have a tendency to really follow equations without understanding where they come from. I think sometimes it's hard to understand where some equations come from, honestly. But if you can have a conceptual, at least a conceptual understanding of where a law comes from, then you have a much higher chance of applying it correctly. Now, I think that these they should be understandable with what we've already covered. They really should be. So let's dive in and see what these laws are all about. So there's quite a number of them. There are 8 here. Here's 4, here's another 4. If you have a signal, this signal is A, so A is the variable, and you add to 1. So we can this one here. So that's like having an OR gate. Okay, you have A as an input, and you always have a logic 1 as your other input. Well, it's an OR gate. You're always going to have a 1 in the output. Remember the truth table? No, 0, 0. 0, 1, 1, 0, 1, 1. Whenever there was a 1 at either input, there would be a 1 at the output. Okay? So if you have a 1 at the input, you're going to have a 1 at the output. Okay? Now say, going on to the next one, OR gate again. You have A, it can be 1 or 0, and the other input is a 0. Okay, so we're talking about either this or this. So if A is 1, the output will be 1. If A is 0, the output will be 0. So it's going to follow along with whatever A is. Okay, so A plus 0 is A. Okay, now we have A and A as inputs, so they can be either 0, but the thing is that if A is 0, that means they're both 0. And if they're both 0, then the output is 0, which is A. Yeah. If they're both 1, the output's going to be 1, which is why a plus a is a. Okay, and then lastly on this one here, we have a plus a bar. So if a is 1, then you're going to have a 1 and a 0, which means that your output's going to be 1. Or if your a is 0, then a bar is 1. So you're also going to have 0 or 1, which means your output's going to be 1. Okay, I hope this is making sense. Now we're moving on to the right-hand side of this table and the AND gates. So here we have, change color, here we have a times 1. So we have a going into an AND gate, and we also have a 1 going into the AND gate. Do you remember the truth table for AND gate? Okay. 0, 0, 0, 1, 1, 0, 1, 1. We only have an output of 1 when both inputs are 1. Otherwise, we have 0. Now we do have a 1 here. So if a is 0, the output is 0. If a is 1, the output is 1. So the output is going to be a. It's going to follow whatever a is. So the next one, we're ANDing a with inputs always low. Now it's an AND gate. Both inputs need to be 1 for the output to be 1. So this is never going to have an output that's high. It's always going to be 0 because one of the inputs is 0. Okay, so a and a. So that means you're either going to have 0, 0, and the output will be 0, or you're going to have 1, 1, the output's going to be 1. So it's going to follow the inputs, which is why you have a and a is going to equal to a. And lastly, have a with the input a bar. So if you have 1, a is 1, then a bar is 0. If you have a as 0, and the other input will be 1. You can't ever get both inputs to be 1 because one is the inversion of the other. Therefore, the output is always going to be 0. Okay, I should make this a before it gets complicated. Okay, I hope that makes sense for the identity laws for simplification.